Hello everyone, this is Teacher Harold, your junior high school math teacher. And in this video, I'll discuss the first lesson in the second grading period, Mathematics 9. And it is illustrates situations that involve variations such as direct, inverse, joint, and combined variations. After watching this video, you are expected or you should be able to illustrate situations that involve variation and express related situations as equations of variations using k as the constant of variation. And of course, you are you should be able to participate actively during the discussion. In this module, you would be able to study the different types of variations as well as some real-life situations modeled by these concepts. There are several relationships of quantities that they or you will encounter in this material. You will learn how to change in one quantity could produce a corresponding change in other quantity or quantities. Let us take the first type of variation, and this is direct variation. If two quantities are related in such a way that an increase in one quantity results in a corresponding increase in the other and vice versa, then such variation is called a direct variation. If two quantities are in direct variation, then we also say that they are directly proportional to each other. Such variation has two types. The first one is direct linear variation, and the second one is direct square variation. Now let us go back to direct linear variation. In symbol, where x and y represent the two quantities, then y varies directly as x, or y is directly proportional to x. Therefore, in translation, we have y equals kx. Okay, from this verbal statement, this is how we translate this particular statement, either this one or this one, into mathematical symbol or equation. So we have y equals kx, or if we transform that equation solving for k, we have k equals y over x, where k is known as the constant of variation or the constant of proportionality. The following examples are situations that illustrate direct linear variation and their translated mathematical statements or equations using the constant of variation k. Number 1. The distance in kilometers traveled by a moving vehicle varies directly as the time the vehicle has been traveling. So for us to translate this situation into mathematical equation, we need to represent the involved quantities from this situation by symbols. Like for example, the distance here can be represented by the symbol small letter d, because since the word distance starts with d. And another quantity involved in this situation is the time, which is denoted by t, since t is the letter that starts with the word time. Okay? So again, let us read the situation. The distance d, represented by d in kilometers, traveled by a moving vehicle varies directly as the time t the vehicle has been traveling. So if we're going to translate this mathematically, we have d is equal to kt. Next, we have number 2, the price of a meat to the number of its weight in kilograms. Suppose the first quantity, which is price, is denoted by small letter p, and the number of weights of that meat, which is in terms of kilo, is represented by small letter w. Therefore, if we're going to translate this mathematically using k, it becomes p is equal to kw. Next, for the third situation that illustrates direct linear variation, we have the number of workers to the amount of work to be done. So the two quantities involved here are the number of workers and the amount of work to be done. So for the number of workers, let us denote that as a small letter m. And the amount of work to be done is denoted by w. So if we're going to translate this mathematically, we have m equals kw. Next, let us have the second type of variation of second type of direct variation. So if we have the linear or direct linear variation, this time let us talk about the direct square variation. Now there are many situations where one quantity varies directly as the square of the other. Such relation between these two quantities is called direct square variation. In symbol, where x and y represent the two quantities, then y varies directly as the square of x. Or we could say this in another way, which is the same as this one, and that is y is directly proportional to the square of x. So either of the two statements, we could use any of those two to translate the statement into mathematical equation. Hence, in translation, we have y is equal to kx squared. And if we want to solve for k, from this equation, we have k equals y over x squared, where k again is known as the constant of variation or the constant of proportionality. In the following examples are situations that illustrate direct square variation, and they're translated mathematical statements or equations using the constant of variation k. The area of a circle to the square of its radius. So the area can be represented by capital letter A, and for the square of the radius can be represented by the symbol r. So in symbol, that will give us A equals kr squared. Next, the distance in meters of a falling object starts from rest to the square of the time in seconds the object has been falling, neglecting the air resistance. So in symbol, first is we represent the two unknown quantities by symbols. So for the distance, we denote that by small letter d, and the time the object has been falling in terms of seconds is denoted by small letter t. So in mathematical translation, that will give us d is equal to kt squared. Third example, the area of a square is directly proportional to the square of its diagonal. So again, for the area as our first quantity, we can denote that by capital letter A, and for the diagonal of a square, that will be our the small letter d. Okay, so again, if we read the situation, the area A of a square is directly proportional to the square of its diagonal d. So if we're going to translate this situation, we have A is equal to kd squared. And these three examples are under this type of direct variation, which is the direct square variation. Okay. Next, let us have the second variation. So we are done with direct variation, so let us take the inverse variation. So if two quantities are related in such a way that increase in one quantity causes corresponding decrease in the other quantity and vice versa, then such variation is called an inverse variation, or sometimes we call it an indirect variation. Now, if we have two quantities under such variation, then we also say that they are inversely proportional to one another. So in symbol, where x and y represent the two quantities, then we can say that y varies inversely as x, or saying this statement in another way, so we have y is inversely proportional to x. Therefore, if we translate this this statement into mathematical symbol, we have y is equal to k over x. Or if we transform the equation solving for k, we have k is equal to xy, where k is, again, we call it the constant of variation or the constant of proportionality. Now, just like the direct variation, there are some real-life situations that involve inverse variations with translated mathematical statements or equations using the constant of variation k. And these are: number 1, the number of days to finish the work varies inversely as the number of men to do the work. So in symbol, so the number of days is represented by small letter d, the number of days to finish the work, and the number of men to do the work is represented by small letter w. So in symbol, we have d is equal to k over w. Next, the intensity of illumination represented by small letter I received from the source of the light varies inversely as the square of the distance denoted by small letter d from the light source. So in symbol, we have I is equal to k over d squared. Next, the pitch of a tone is inversely proportional to the wavelength of the tone. So the two quantities are the pitch of the tone and the wavelength of the tone. So let us denote the pitch by a symbol small letter p, and the wavelength of the tone is denoted by small letter w. So in symbol, that will give us p is equal to k over w. Okay? Next. Actually, we have two more examples under inverse variation. Let us proceed. The speed of a moving vehicle varies inversely as the time it covers a fixed distance. So, the speed can be denoted by small letter s, while the time can be represented by small letter t. So, if we're going to translate this into mathematical symbol, we have s is equal to k over t. Next, the weight of the body above the Earth's surface and the square of its distance from the Earth's center. So the weight is denoted by small letter w, and the distance from the center of the Earth is small letter d. So by their symbol, we can translate this situation in number 5 into mathematical equation under inverse variation. So that is w equals k over d squared. Okay? Next, we have the remaining types or kinds of variation, and these are the joint and combined variation. Now, each of these types involves three or more quantities. A change in one quantity produces a proportional change in the other quantities. Okay, let us start with the joint variation. So it describes a situation where one quantity depends on two or more other quantities and varies directly as each of them when the others are held constant. So if a certain quantity varies directly as the product of two or more than two other quantities, then the relationship among these quantities is known as the joint variation. Like for example, say Z varies jointly as X and Y. This is the same as this statement. Z varies directly as the product of X and Y. So if we're going to translate this mathematically, inserting again K as the constant of variation, so we have Z is equal to KXY. And K is again known as the constant of variation. Some related situations with translated mathematical statements or equations using the constant of variation K. Okay. Number one, the force exerted on the object varies jointly as the mass of the object and the acceleration produced. So if force is represented by capital letter F and the mass is by small letter m, together with the acceleration as small letter a, then mathematically speaking, the equation of this situation is what? F is equal to kma. Next, situation number 2, the area of a triangle varies directly as the product of the base and the height. So if we denote capital letter A as the area of the triangle, and the base a small letter b, and the height a small letter h. Therefore, under joint variation, the mathematical symbol is what? A is equal to kbh. Next, number 3, the kinetic energy of an object varies jointly as the mass of one object and the square of its velocity. So, the kinetic energy can be denoted by capital letter E having a subscript of K, and the mass is small letter m, and the velocity is small letter v. So, in mathematical symbol, we have E sub k is equal to kmv squared. Next, combined variation. If a certain quantity varies jointly as the other quantity or product of two or more variables, and inversely as another variable, then the relationship among these quantities is known as combined variation. The following are combined variations at least three quantities represented by variables using the constant of variation K. First one is Z varies directly as X and inversely as Y. So, at instant, we have the corresponding mathematical translation of this statement. Next, P varies directly as the square of Q and inversely as the cube of R. Okay. Third one, R, capital letter R, varies jointly as A B, and C, and inversely as capital letter A. Take note, small letter A is different from capital letter A. Okay? Although they are of the same letter, but you will notice that the first K is written in the lower case and the other A is in the uppercase, meaning they have different representation. They are not the same. Okay? So, if you don't have any question, let us proceed. Okay, joint variation. Again, we are still under these two remaining types of variations. So, for the combined variation, okay, we have some situations under such variation, and they are mathematically translated using the constant of variation K. The first one is the average number of phone calls per day between two cities varies jointly as the populations of the cities and inversely as the square of the distance between the two cities. So, there are quantities involved. Okay, the average number of phone calls, so that is denoted by capital letter C, between two cities varies jointly as the population. Okay, the populations, so that is P sub 1 and P sub 2 of the cities, and inversely as the square of the distance. Probably this is small letter D. Yun. Okay? Now, this is the situation under combined variation, and this is the mathematical translation. Next, the volume of a gas, which is denoted by capital letter B, varies directly as its temperature and inversely as its pressure P. And this is the translation. Okay? Okay, so I think we are done with the discussion. And after a few minutes, I'll give you the set of activities for you to work on. Probably the activity or the set of the set of activities that I'm going to provide you will be your first set of assignments or seat work. So for now, I'll see you next time.